So Dalton's law is basically just the sum of the partial pressures. And you can solve for these pressures a multitude of ways, but the most common way is the ideal gas law. All right. So the ideal gas law is, it's PV equals nRT. But in this particular case, if you want to solve for the pressure of the first gas, you have to know the moles of the first gas. Same thing for the second gas. You got to know the moles of the second gas. Now, this is if you want to solve for the individual pressures. All right. And so we did several examples that use the ideal gas law. So now let's say, for example, that you knew the moles and you wanted to know the total pressure of the system. Well, what you could do is instead of taking these two individuals and then adding them together, which is fine, you could actually take this equation here. So the Dalton's law can be really broken down into three different equations. The first one is the main one. The second one is where you calculate the individual pressures. And the third one is where you can calculate the total pressure. So but again, the importance of this is that the sum of the individual pressures equal the total pressure of the system. Now, and that takes into consideration both gases, N1 and N2. All right. So I would recommend that is something you ought to put down on your note card. All right. Now the example I give you is here. All right. So now I what I want you to do is I want you to work on this problem. I really want to do root mean square velocity today because that's something that is more important than this because we haven't seen anything like it. This problem basically revolves around the ideal gas law. It revolves around using these three equations that you see here. And so what you have to be able to do is you have to be able to look at the problem. And this is the challenging part of this problem because there's so many different numbers and variables in here. What you have to be able to do is you have to be able to distinguish what to use first and then second. Now, in the solution down here, what I've done is I've written it out point for point as how to approach solving for it. You'll see that in this example, I have to solve for the moles of each of these. And then once you know the moles, you can solve the pressures. Once you know the individual pressures, then you utilize the equation from Dalton's law. So I know that we've kind of gone through that fairly quickly, but does everyone have some comfort in how Dalton's law is used? Everyone good with this equation here and what it means? So again, Dalton's law is a sum of the partial pressures. All right, you guys are gonna have to respond to me through the chat box. That's the only way I know you're with me. All right. Now, let's see here. We're getting close. The mole fraction. Let's do. So go ahead and do me a favor. If you've taken notes, go ahead and jot this equation down. There are two other equations here. You can jot those down later, but you definitely want to get this one here. We're going to do an example of this one in just a minute. So I'm going to come back about 10, 18, and we're going to start working on an example. So go ahead and get this top part written down. So you can see a few notes I put on the board here where we have the mole fraction is equal to the moles of the individual gas one divided by the total moles. Now keep in mind that in order to calculate the moles, you still have to go back to that roadmap that we learned back at the beginning of the semester where you can convert grams into moles. So let's say you start off with 25 grams of sulfur gas and a sample of 400 grams of, of gas. Now, the 400 grams, we're just going to kind of try to make that easy. We're going to say, so if we have 25 grams of sulfur gas, and let's say that 400 minus the 25 gives me 375 grams of the other gas, and the other gas is going to be composed of CO2. All right. So what is the mole fraction of sulfur? What is that equal to? All right. So in order to answer this, what we need to do is we need to figure out how many moles of sulfur are present divided by the total moles. All right. Now, so sulfur, there's 8 of those, and each sulfur measures out at 32. That makes the molar mass of this to be equal to 256 grams per mole. All right. So 25 divided by 256 gives me 0.0977 moles of sulfur. All right, now we're going to do the same thing for that of CO2. All right, now there's 375 grams of CO2. We're going to divide that out. So 12 plus 32 gives me 44 grams per mole. All right, so 375 divided by 44 gives me 8.52 moles of CO2. So we have enough now to get the mole fraction figured out. So the mole fraction of sulfur is equal to 0.0977 moles divided by 0.977 plus the 8.52. You can see this isn't going to change it much. So we should expect a pretty small number here. And that gives me a mole fraction of 0.0113. Now the mole fraction has no units, all right? So there aren't any units. Boys, quit. All right, so that's how you get the mole fraction, man. It's that simple. Now, if you know, so let's say, for example, the total pressure, just gonna pick the number off my watch here. So let's say that the pressure for today was 29.55 inches of mercury, and we wanted to figure out what the partial pressure for the sulfur gas would be. So what we do is you can take this 0.0113 and you can multiply it by the 29.55 inches of mercury, and you can actually figure out what the partial pressure of that gas is. So, and that means that would be 0.335 inches of mercury. Now, so that's one advantage to knowing the mole fraction. And then you can figure out the partial pressure of the CO2. So what you can do there is you take the total pressure, the partial pressure of the sulfur, just subtract it out. All right, so these problems get to be a little bit fun when it comes to just using what you know and what you're given and figuring out the other parts. So that would be the partial pressure of CO2. I swear, I'm gonna knock your head. Come here. Here, come on. Come with me. Okay. So that's dealing with mole fraction. Any questions on that? Yeah, I'll show you the troublemaker, and I won't make it. I'll make it very short. Let's see. I don't know if y'all can see me or not, but this is the troublemaker causing all the problems. Yeah, you're trouble causing me problems here in the class. This is why I don't bring them to work. Yeah. Everybody likes you, but they don't realize what kind of terrorize you are. Huh. No, the Huskies can be a little challenge, especially when they're brothers and they want to fight each other over toys. Yep. Oh yeah, they are cute, but they have their moments. So, all right, let's go back to this page here. So we are going to jump into this. So what I want you to do right now, I want you to write down. So look at my mouse, write down these two things, and then the very last equation here. So these two things and the very last equation. I'll come back in a couple minutes and then we'll start working and making sure you know what those mean and stand for. All right. So no, it's actually a different R value. So I'll put it here in the chat box. So the R value that we use for the root mean square is 8.314. Yep. 8.314. Oh, let's see here. Y'all can still see it though. Look in the chat box. Yep. And then don't forget the units there. Those are also important. So the reason for that being is that there's a conversion factor that goes from the joules to liters and atmospheres, and that's why they're different numbers, Cal. But you don't have to. You don't have any. You don't have to know how to do that. All you have to know is the difference between the two. So ideal gas law is 0.0206, and then root mean square deals with the 8.314. So just that is actually something that you should write on your note card. I would definitely put that on your note card. All right. Now, something else that you need to make sure you write is the fact that molecular weight should be Now, typically we have units of grams per mole for the molecular weight, but you need to make sure you convert to kilograms per mole. All right. And that is the one thing that I would say gets people the most is that they don't do that conversion. All right. So you got to make sure that your units are correct in kilograms per mole. All right. So uh, everyone let me know when you're ready to move on. I'm just kind of waiting on everyone to finish writing this stuff down and taking some basics. Y'all let me know when you're done and I'll move on. This here, Tiara. See where I'm circling it? So you need to have this and then this. All the other stuff, don't worry about it. What does that mean? How much time do we have here? Yeah, that's the problem with this program is it cuts me off. So I've got 10 minutes left here on this program. What I'm going to do is when it, right, exactly. So when this time runs out, I'm going to log back in and then what way it gives us the rest of the time we need. So everyone make sure you use the link that I give you on Canvas. All right, I'll send you a link. If it don't happen, it don't happen. So if worst case scenario comes up, you're gonna watch the rest of the videos and the what is that talking? Sebastian. There we go. All right. Okay, so let's do some examples up before we run out of time. Okay, so now we're gonna look at hydrogen gas, and then we're gonna look at methane gas. All right. Now the question is, which is gonna have a higher root mean square velocity? Okay, so that what we're gonna do is we're gonna calculate the root mean square velocities for each of these. Okay, so which one's gonna move faster? Now, hydrogen gas is 2.016 grams per mole. I'm just going to go ahead and calculate it for you. That one's pretty easy. And then this one is 16 grams per mole. Now, based off of just basic observations through time, we always have seen that lighter molecules are going to move faster than bigger molecules, right? If you ever want to get chased by a bear and you don't want to get eaten, just take a person that's heavier than you. You can outrun them, right? I know it's a terrible way to do it, but it's survival of the fittest, right? So don't tell nobody I said that. So what we're gonna do is we're gonna figure out the root mean square velocity for hydrogen gas first. All right, so I can already see what someone's gonna say in the chat box. Oh yeah, classic joke. Yep. So here's the thing. We're going to have square root of 3 times R, which is 8.314. And then we're going to have 298 Kelvin. If I do not give you the temperature, your temperature will be 298 Kelvin. All right. So just make sure that's something you write down. All right. Now the molar mass is 2.016, but we cannot use it in grams. So we're going to divide that out by 1,000, which is going to give me 0.002016 kilograms per mole. All right. So now in your calculators, what you should do, and seriously, this is something that you need to pay attention to, is in your calculator, it's going to pull up the square root. All right. And what you need to do is type it exactly the way that I'm showing you here on the screen. Close that out. So, yeah. and then hit enter. All right. So when you get this, so I want you guys to calculate this. All right. So calculate this and put your answer in the chat box. Pretty much. So when you get your answer, put it in the chat box. I'll give you the first number. All right, Josh. Looks like he's got it. Let's see here. Something else I better do right now before I forget here. So I'm sending you guys a link here in the chat box. Go to that link and sign in. All right. When we get done here, which you have 5 minutes, go sign in. Okay. All right. Thank you, Harley. Is that right? Yeah, that's pretty darn. Now it looks like yours is much higher. What did you do different, Harley? Okay. All right. So you just okay. So yep.
I typed too many twos.
I see that. I see that. Thank you, Harley. Is everyone else getting this? All right. Now, the next thing I want you to do is so we have the first one, and I'm just going to go ahead and write this down. So it's 1,920. All right, and that's going to be meters per second. So we'll talk about the units in class on Wednesday. The second one I want you to do is the one for the methane. All right, so we got the one for hydrogen gas. Let's do the one for methane now. So the difference here, the top part stays the same. It's the bottom part that's changing. All right, so go ahead and plug that in. In fact, if you're smart with your calculator, if you hit second enter, it'll bring up the stuff you just wrote, and all you have to do is just change out the part for hydrogen to methane. And what you'll get is 682 meters per second. All right. Let me know if you get that. Make sure you guys double check with me there, please. All right. Yeah. Okay. All right. Good. So does that make sense? So I'll just read what I wrote down there. Lighter molecules move faster and will have a higher root mean square velocity. Does everyone understand that? Any questions on the calculation part? Okay. So I'm gonna go ahead and just call it here. I don't really have enough time to go into any other details, so I'm not gonna worry about trying to get it started back up because by the time we get started back up, it'll be the end of class. So just make sure everyone gets signed in using that link. Make sure you guys get signed in so that way you get credit for being here. All right. So what we'll do tomorrow is we'll work on the lab that is the concentrations by spectroscopy. So make sure that you read up on that lab and you come prepared. All right. And oh dear. So watch the videos, read the lab, come tomorrow prepared. Wednesday we will finish it up. Friday you'll have a test. All right. So y'all have a good day and I will talk to y'all later. I'll see y'all tomorrow. Bye guys.